Hi, my name is Tancred. I am a young researcher at the University of Edinburgh, and I am in charge of the research project you are looking at. The main objective of this research is to improve our knowledge on the oceanic and atmospheric systems responsible for past climate change at the southern hemisphere's mid-latitudes. This is important because understanding these natural systems better is key to better predicting future climate change in this region of the world. And because mountain glaciers are great tools to study past climates, we want to reconstruct for the first time the glacial history of northeastern Patagonia over the past 1.5 million years. The reason why we study in Patagonia is because simply it is the only continent located on Earth at those latitudes. The rest is all ocean. Technically, we are going to determine the age of former Patagonian glaciations using a dating technique called Cosmogenic radionuclide dating. And I'll be talking more about this in the rest of this video, in the second part. For this climate reconstruction to be robust and useful, we need to date all the preserved glacial advances that we can find on the field. And that represents a lot of time on the field, a lot of data gathering, and therefore a lot of money. My team and I have been to Patagonia in 2019, and we have collected on the field about half of the data set, half of the glacial deposits. And we are currently processing those samples in the lab. However, we are struggling to find all the money to organize a second expedition to Patagonia, complete the sampling, and bring this study to its full potential. So if you're interested in climate science, in glaciers, and in this particular project, then my team and I would be very grateful if you could help us financially in order to go back to the field and complete the story. Thank you so much in advance for your help and your support. And if you would like to have more information on this research project, then you can either keep watching this video, or you can find also plenty of details on the Crowd.Science webpage. Bye. Glaciers are extremely sensitive to climate change. This video is an accurate model simulation of the past glacial behavior in the European Alps over the past 120,000 years. Time in thousands of years is in the top right-hand corner, while temperature relative to today's is shown by the black line. When temperatures drop, more snow accumulates in the mountains, and suddenly glaciers grow far into low-lying valleys. On the other hand, if temperature rises, one can see that those same glaciers retreat towards the higher mountains they came from. Today, those alpine glaciers are tiny remnants of what they once were, and their demise is increasingly rapid. As this simulation demonstrates, glaciers are fantastic tools to reconstruct past climate change. My team and I aim at using past glaciers to reconstruct the past climate evolution of the southern hemisphere mid-latitudes, a region of the world for which climate-forcing mechanisms are poorly understood. The only place where this can be done is Patagonia, the southern tip of South America. Although the present-day Patagonian glaciers are confined to small, isolated white patches that we can see here, during the last ice age, the Patagonian Andes were host to an enormous ice sheet, the biggest in the southern hemisphere outside of Antarctica. This diagram shows you the approximate extent of the former Patagonian ice sheet during its last major expansion around 20,000 years ago. Over the last ice age, the past 2.6 million years ago, this ice sheet expanded and collapsed many times over. The arid conditions and low population densities of the Argentinian desert in which Patagonian glaciers advanced allows for one of the most well-preserved glacial landscape in the world. Those glaciers are totally understudied. For instance, there are currently almost no published studies reconstructing glacial advances in the area presented inside this yellow box, which extends for over 800 kilometers. My team and I at the University of Edinburgh are determined to reduce this data gap by studying those extinct glaciers and their former behavior. We focus our study on a valley system which was once host to the Rio Corcovado and Rio Remo glaciers, RC and RH, flowing along the path of those red arrows. Those glaciers have never been studied in detail before. On this topographic map, one can see circular features located near the end of the arrow labeled RC after Rio Corcovado. Those features are called terminal moraines. When cold and wet climates enable glaciers to advance, those will erode entire valleys like bulldozers. The tremendous volume of rocks picked up will be transported within the ice over hundreds, thousands of kilometers in some cases, before reaching the terminal margins of the glacier, where it will be deposited on the ground. During a significant period of stable climate, a glacier doesn't advance nor retreat. All the sediment transported in the ice will accumulate at the same terminus location and form a ridge outlining the margins of the glacier. If warming conditions causes the glacier to retreat, the ridge is left behind and, given certain conditions, can be preserved for thousands of years, hence allowing us to assess the former silhouette of the extinct glacier. This is the case for our chosen valley, which, as one can see on the right-hand diagram, presents numerous well-preserved terminal moraines. This picture, taken by myself from the Rio Corcovado Valley, shows you an example of one of those prominent ridges, which is here intersected by this road, but continues and extends towards the mountains in the background. Our work consists in dating the formation of those preserved moraines, and therefore reconstruct the timing of ice sheet expansion in this unstudied region of Patagonia. To achieve that, we use a relatively new dating technique called cosmogenic exposure dating. When a boulder falls off the melting ice into a pile of debris, it is exposed to the sky and to incoming cosmic radiation from outer space. This invisible radiation bombards the surface of a boulder and causes elements that make up our boulder's minerals to split open, leading to the creation of new, rare elements such as beryllium-10. As long as the boulder remains exposed to the atmosphere, beryllium-10 slowly accumulates inside our boulder's minerals. By sampling the surface of that boulder and conducting a complex analysis to determine the concentration of beryllium-10 in that rock, we can establish when beryllium-10 started accumulating, which tells us when the boulder was first exposed to the atmosphere, which in turn tells us when the glacier reached this location to deposit that boulder. Consequently, this concentration will give us the edge of our glacial advance.